Welcome to session 12 of electronic structure theory. In this session, I'll be talking about not wave functions and energies, but what are called the responses of these quantities to various perturbations. This is called response theory. And the main kind of perturbation that I'll be talking about is deformation of the nuclear framework. That is, if you have a molecule, for example, sitting at its equilibrium geometry, and you think of distorting the bond lengths or bond angles by small amounts, you want to think about how does the energy change when you carry out these deformations. That gives you some idea of what the energy landscape, the energy profile looks like as a function of those deformations. And this relates to, for example, vibrational frequencies, because vibrational frequencies have to do with the molecule moving under the approximately harmonic restoring force of the chemical bonding framework. But it has also to do with reaction energy profiles. When we talk about reaction paths and finding transition states and moving along the reaction path from a transition state to the products or to the reactants, we're talking about how the energy landscape profile evolves as a function of molecular deformation. So in session 11, we'll be doing response theory, focusing primarily on the response of the electronic energy to deformations, stretchings, and chemical reactions, and bond breakings and bond formings. Those are the kind of deformations that we're talking about. So response theory is relating to spectroscopy, vibrational frequencies, and to chemical reaction dynamics, transition states, and reaction paths. Welcome to session 12 of electronic structure theory. This session has to do with what we call response theory. And before going and starting all these equations that I'm going to be talking about, let me just try to motivate this a little bit, Diane. So response theory basically has to do with the following. And so far when we talk about electronic structure theory, we talk about calculating an energy of a molecule or maybe a wave function or something like that. In response theory, what we say is that experiments often are not interested in the energy, they're interested in how the energy responds to certain things. And just as two examples, if you talk about vibrational spectroscopy, what you're talking about is, that potential energy curve. And so the curvature of that curve near the bottom, gives rise to the vibrational frequency. So what you're talking about there is how does the energy respond if you compress or extend the bond length a little bit. So you're actually interested in like derivatives of the energy with respect to, in that case, it would be geometrical deformations of the molecule. So that has to do with vibrational spectroscopy. But also, potential energy surfaces where you do transition states are responses, because if you take the molecule and stretch a bond and go up to a transition state, you're doing a response of an energy to some deformation. So that's one context in which response theory will come into play. But another context is, for example, when an experimentalist measures the dipole moment of a molecule. How do they really do that? Well, what they do in the gas phase dipole moment measurements is they take the molecule and they pass it through an electric field. And if the electric field is inhomogeneous, meaning it's different in different points in space, that will tend to deflect the molecule. And the deflection of the molecule will be a result of the force that the electric field exerts on that molecule. And force is the derivative of the energy with respect to position. So again, response, that is, how does the energy depend upon, in this case it would be electric field, in the earlier case it would be deformation of a bond. So that's what we mean when we say response theory. It means sort of like, essentially what it means is derivatives of the energy with respect to certain things that relate to the kind of experiment that you want to study. So the first thing that I want to talk for quite a bit about is the derivatives of the energy with respect to molecular deformations. So in this first slide here, I talk about analytical expressions for the derivatives of the energy with respect to vibrational distortions. So for example, if we label, we have some big molecule. It could be a polypeptide. It could be an HF molecule. Doesn't matter. But each atom in that molecule has a set of 3 Cartesian coordinates, x, y, and z. All those coordinates together we call x sub k. So for example, for an HF molecule, x1, x2, and x3 might be the xyz positions of the hydrogen atom. x4, x5, and x6 would be, for example, the xyz coordinates of the fluorine atom. For a big molecule, of course, this x vector would be 3n long. It will be the number of Cartesian coordinates of the entire molecule. And what we're after then is, when we talk about derivatives, the first derivative, for example, gk being the derivative of the energy with respect to xk, We call that the gradient. This is how does the energy change if we take the kth coordinate and move it a little infinitesimal amount. We call that the gradient vector. The second derivatives, because sometimes we're interested in, when you're, for example, trying to find a minimum on a potential energy surface, you want to find a point on the surface where all the gradients are zero, because you're at the bottom of this minimum, so the derivative in any direction is zero. But if you want to make sure that you're actually at a minimum, you want to make sure that the curvature along all coordinates is positive, so you're not at a maximum. And so sometimes you have to look at second derivatives. We call that the Hessian. So the matrix that's formed by taking the second derivatives of the energy with respect to, say, xk and xl, we call that the kth element of the Hessian matrix. That would be 3n by 3n in dimension. Now, a long time ago, before people came up with analytical expressions for these energy derivatives, gradients and Hessians, they were evaluated by what's called finite difference. And this just means people would take a molecule, they'd actually take an atomic coordinate, and they would move it a tiny bit, let's say in the x direction, plus or minus, and just calculate the energy at those different points and subtract the two divided by the amount that they moved the nuclear displacement, and that would be like a finite difference approximation to d coordinate. But these days we have analytical expressions for doing these things, and I'll be talking about those expressions. But first of all, let me just talk about, so that what I want to do today in this session is talk about, given the gradients and Hessians, what can you use them for? And then secondly, how do you get the gradients and Hessians? Where do they come from? What's the analytical expressions for them? So first of all, what do you do to use them? So here I say, suppose you had these gk for a hypothetical molecule, k going 1 to 3n, and you had the Hessian matrix, what could you do with it? Well, one thing you can do is to try to find minima on a potential energy surface, and this is very common. We say geometry optimization. That's what this is. So what you tend to do is you say, I have a certain point where I'm going to start. We call that x0. So it's just the x1 through x3n coordinates of the nuclei that you are starting with. When you say, I'm going to guess the geometry is this. So that's your initial guess. What you then do is, if you have the gradient available, suppose you have the gradient vector g1 through g3n. Well, what you can do, this is the simplest thing that's possible, is if you just think about what the gradient means, it means that if I take a step in the positive direction of component k, then if that gradient is positive, that means the energy is going up. dE dx being positive means if you increment x, the energy is going up. So the simplest thing to do to find a minimum, to try to find a minimum, is to take little tiny steps. Delta xk equals minus a small amount times the gradient. So in other words, if the gradient's positive, you take a step of magnitude that's proportional to the gradient, because if the gradient's saying that the energy is way up and steep in this direction, then you say, I want to not go that direction, I want to go the opposite. So that's what the minus sign is there. So what you tend to do is, for those directions where the gradient's positive, you go backwards. For those directions where the gradient's negative, you actually take a positive step along that direction. So you take steps that are along the gradient and with a magnitude that can be controlled by this a parameter. Now you say, what's the relevance of that? Well, if you have the gradient, you just know locally what does the energy surface look like. You don't want to go take a 25 angstrom step, because 25 angstroms from here, the geometry of the molecule will have changed tremendously. So you use this a parameter to control the total length of the step that you're going to take. And you might make it so the a parameter makes the total step length be, say, 1/100th of an angstrom total. So that's the old-fashioned way of doing things. And if you just take and you say, well, that delta E would equal dE dx times delta x, and if you use this formula for delta x, then for delta E total you would get minus a times the summation over all the components of the gradient times gk squared. So this will essentially say that you would predict the energy will go downhill, and the amount it will go downhill can be controlled by that a parameter. So this is the simplest old-fashioned way of people were using, and it's sometimes still used in molecular optimization or geometry optimization programs. This is the simplest thing you could do if you just know the gradient. Take steps opposite the gradient is what we say. Okay, now one of the problems with that approach is that, and it often works, but the problem with it is that if you take a series of steps, and I just want to go back to this transparency here, so what you tend to do is you make an initial x0 guess, you evaluate the gradient at that point. Then you take little tiny steps delta xk given by this formula, opposite the gradient. And then what you do is you go to that new geometry that's x0 plus the delta x, and you do the whole thing over again. You calculate, pretending this is now x0, a new gradient, and you take another step, and a little baby step, baby step, baby step. And as long as you go downhill continually, and you eventually get to a point where all the gradient values vanish, you say, oh, I'm at a minimum. The problem with that is you hope you're at a minimum. And on this picture here, I'm showing just a hypothetical two-dimensional. Now this is, you say, that looks pretty complicated. What we're dealing here with is a 3n dimensional space, these xk's. So this is just a simple little depiction in 2 dimensions. And the idea basically is that on this surface we have a minimum that's over here in the bottom left-hand corner, but we also have points where the gradient vanishes, like at the top here, this so-called second-order saddle point. See, that's something that's a maximum in 2 directions, and that also would be where the gradient vanishes. So you can't be sure when you find a point where all the components of the gradient vanishes that it's a minimum. You have to be able to, at that point then, go and evaluate the second derivatives to see, are you at a point where the second derivative is negatively curved, or are you at a point where the second derivative matrix is positively curved? So usually what we have to do is once we find a minimum, or we think we found a minimum, we have to then make sure all the gradient components vanish at the minimum. That's necessary. But then what we do is we calculate this Hessian matrix, second derivative matrix, and what we do is we find the 3n eigenvalues of that Hessian matrix. Now when we do that, 6 of those eigenvalues will turn out to be 0. Why? Because what they are is they are eigenvalues that have to do with translation and rotation of the molecule. That is, if we have any hypothetical molecule, we know that we could take that molecule and we could move, for example, we could increment the x-coordinate of all of its atoms by a meter. And the energy shouldn't change because we haven't distorted the molecule. Or we can increment all the y parameters of or coordinates of each nucleus, all the nuclei, by a meter, and the energy shouldn't change. So the energy of the molecule is invariant with respect to translations along 3 axes and with respect to 3 rotations if it's a nonlinear molecule. So what we'll find is that in this Hessian matrix, if we evaluate it 3n by 3n, 6 of its eigenvalues, translation and 3 rotations, will be 0. And in a sense, they're not interesting to us. What we want to make sure, though, is of the 3n minus 6 remaining eigenvalues, if we want a minimum, we damn well better not see that any of those 3n minus 6 eigenvalues is negative, because if it is negative, it means you've found a point where, at least in one direction, the Hessian matrix is negatively curved, which means that you're sort of at a maximum along that direction. So, for example, at a minimum, we would find all the gradient components vanish, like at this bottom left-hand point here. And we would find all 3n minus 6 eigenvalues of the Hessian matrix would be positive. At the second order saddle point, we would find all components of the gradient vanish, and 3n minus 8 components of the Hessian would be positively curved, but 2 of them, like the 2 shown here, would be negatively curved. One of the important points we have to find later on, and we'll talk about this later on, is transition states. And on this blue plot that I've shown here, you can sort of see that there's transition states connecting you from this lower left-hand minimum up over a first-order saddle. Now, first-order saddle means that there's one direction that's negatively curved, and all other directions orthogonal to it are positively curved. It's like a mountain pass. So up over this mountain pass labeled the transition state here, if we want to find that point, that's a point also where the gradient vanishes in all directions. In one direction, it's negatively curved, and in other directions, it's positively curved. So that's how we have to use the Hessian matrix, is to look at the curvature of our points that we identify. Okay, so to do really modern, up-to-date geometry optimizations or finding reaction paths or finding transition states, you really need to know just that you have to use the gradient vector and the Hessian matrix. And to make things simple here, that is to describe, as most people do when they talk about moving around on potential energy surfaces, instead of talking about moving the Cartesian coordinates of each atom as the 3n independent variables, we tend to think about and talk about what are called the eigenmodes of the Hessian. And just physically, let me go back to this blue picture, What I mean by that is if you were at, say, this first order transition state in the upper right-hand corner of this blue picture here, what I'm talking about is at that point where the gradient vanishes, you can see that one direction is negatively curved to the right and to the left, goes down to reactants, goes down to products. But transverse to that is perpendicular to it, there's another direction that's uphill on the left and uphill on the right. Well, those unique directions that are downhill and uphill are called the eigenmode directions of that Hessian matrix. Mathematically, the way that we get these eigenmodes is we take the Hessian matrix and we find its eigenvalues labeled lambda A, not the zeros, but the 3n minus 6 non-zeros, and we find those eigenvectors. So the 8th eigenvector obeys the summation over L, HKL, VL for the 8th eigenvector equals lambda A, the 8th eigenvalue, times VKA, the kth component of the 8th eigenvector. So we find these eigenvectors and eigenvalues. And what we're looking for then is when we do this, if we actually take the 3n by 3n Hessian matrix, as I said before, we'll find that 3 of those eigenvalues will be 0, and their eigenvectors will correspond to translations. What I mean by that is the eigenvectors that correspond to translations will look like the following. If they will look like, for example, 1, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, and so forth. That will describe motion of the x component of every atom in your molecule along the x direction, just uniform motion along the x direction. Another eigenvector will look like 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0. That's motion along the y direction, and so forth. So the eigenvectors corresponding to translation and rotation will have 0 eigenvalues. You ignore them and don't even do anything with them. But that's what they'll look like if you try to look at them. The other eigenvalues, though, the 3n minus 6, 3n minus 5 for linear molecules of these lambdas, are the things that you'll use to describe whether the molecule is having a stable restoring force, that is positively curved, or is negatively curved. Okay, so what do we do with these things? We just want to play a little bit of algebra now, just to show you the kind of algorithms that we use to actually take geometry optimization steps beyond the simplest thing I talked about earlier, which is look at the gradient and then go in the opposite direction of the gradient. When you have Hessian information, here's what you do. In your brain or in your derivation, you say, look, I know that I would predict a change in energy from the point where I am now, given the gradient information, to be nothing but the summation over k of the gradient component along the kth direction times the step that I would take along the kth direction, delta xk, plus a half the summation hkl delta xk delta xl. That's what you would predict for a change in the energy if you took a certain step along the kth and lth directions. Now, what we tend to do is, and because this matrix H sort of has all these off-diagonal components, we like to re-express this energy expression as 3n minus 6 separate energy changes along these so-called eigenmodes. And I just want to explain how we do that. We pretend that we found the eigenvalues and eigenvectors of the Hessian. And the eigenvectors, of course, are orthonormal, which means that, for example, this equation I've written here, that if I take the 8th eigenvector and the bth eigenvector and I take their dot product, summation over k, VAK, VBK, I get delta AB. They're orthonormal. Why? Because the Hessian matrix is symmetric. They also form a complete set. That is, they obey an equation that says if I sum over all the eigenvectors A and I take VKA, VLA, that is the kth component of eigenvector A and the lth component of eigenvector A, summed over all eigenvectors A, I have delta KL. That's the so-called resolution of identity or completeness relation. Now, the reason I go through that little bit of algebra is we like to express the changes that we take not in terms of Cartesian steps along the kth direction, but instead in terms of steps delta VA along the ith eigenvector. And the relationship between a step delta XK and the step delta VA is given in this bottom line. And it's pretty easy to show this. All you do is you say, okay, delta XK is obviously the summation over L of delta KL times delta XL. That's obvious, because delta function. But then for this delta function, you substitute this equation above here where you've written this delta function in terms of these eigenvectors. So VKA, VLA. And what you then do is you say, well, this VLA times delta XL, that's essentially the dot product of the step vector delta XL dotted into the 8th eigenvector. And that's the component of the step along the 8th eigenvector, which we call delta VA. So the bottom line is, by using that little step there, see what we're going to do is take this delta XK expression in terms of delta VA, we're going to substitute that back into this top line for the delta E energy change. And when we do it, so we take this delta XK in terms of delta VA, substitute it into the expression for the delta E formula, and what we get then is another expression for the delta E formula that I've written in red here. And it's nothing but a summation over A of the component of the gradient along the ith eigenvector. So here's our gradient vector, GL times VLA summed over L. That's just a dot product giving the component of the gradient along the 8th eigenmode. So we're just saying summation over eigenmodes of gradient component along 8th eigenmode, step along 8th eigenmode, plus a half eigenvalue, that comes because this Hessian matrix, times delta VA squared. So the main point here is, this just allows us to think of and to express our energy change as a linear combination of independent. See, it's summation over A, and for each eigenmode A, we have something that's a linear plus quadratic change that's related to the step that we take along the 8th eigenmode and the step squared along the 8th eigenmode. So we can think of these steps as being 3n minus 6 independent steps whose character we can control separately. So what do we do? Well, at the top of this thing, I've just repeated that expression, that the change in energy will be a linear term and a quadratic term along each of these separate eigenmode directions. Well, suppose somebody just came to you with a calculus problem. They said, I have a formula that says G times delta plus a half lambda delta squared. You say, well, you have something that's linear plus quadratic. I say, fine. Would you please find, for example, the minimum in that? Now, why might I be talking about that? Because if I say that this is the way my energy surface looks along the 8th direction, I might be saying, please, along the 8th direction, go and find a minimum. Well, if you wanted a minimum and you knew the thing was linear plus quadratic, you would just say, at the minimum, its derivative, its slope should be 0. So we could differentiate this thing with respect to the delta, the delta VA parameter. We could set that equal to 0. So take the derivative of this with respect to delta VA, set it equal to 0. You would get 0 equals GA plus the half would get canceled by this 2, and you'd have lambda A times delta VA. If you solve that for delta VA, you'd get delta VA is minus G over lambda. So this tells you that if you want to find a minimum, you should take a step along the 8th direction that's minus, that sort of makes sense, opposite the gradient, minus the gradient divided by the eigenvalue of that 8th mode. See, what's different here compared to what we had just a little while ago, as we said a little while ago, that if along this direction the energy is going up, what I want to do is I want to go backwards. Okay, this still has that same algebra in it. Take a step that's opposite the gradient. If the gradient is down, which means GA is negative, then change the sign. So GA times a minus will give plus, which means go along that direction. But this says don't take the same kind of step along each direction, like in the first equation we had some slides ago. This says that if the 8th direction has a very large Hessian eigenvalue, what that means is it's very stiff. The curvature along that direction is very steep. Then it says, along that direction, go opposite the gradient, but divide it by the magnitude of that eigenvalue. So if it's very steep, don't take a very long step along that direction. Why? Because if it's steep and you take a big step, the energies go way, way, way up if it's very steep. And you don't want the energy to be changing that much because you can't trust this approximation of linear plus quadratic except in a little narrow window around where you're sitting now. So that's the physical interpretation of this result here. It's a way you can take a better step than just using the gradient information. So when you do that, you take this expression for delta VA minus G over lambda, you plug it back into the energy change expression, and this tells you, when you do that, that the energy change will be GA delta VA plus a half lambda A delta VA squared. Put the delta VA in there, you get delta E equals, you go through the algebra, and it ends up being minus a half the summation over each independent mode of the gradient squared, that's positive, divided by lambda A. And you say, oh, that's good. Because if I want to go to a minimum, as long as all those lambda A's are positive, this expression here is telling me that the delta E will be negative. So I will be going down. Uh-oh. But what if there's a direction, like on that blue curve? What if I happen to be up in a region where in one of the directions it was negatively curved? If that's the case, this lambda A will be negative along that direction and the energy will go up. So if I use an expression like this for the energy step, the energy will go down along all directions that are positively curved. So along those directions you'll be going down toward a minimum. But if you're in a region that has a negative curvature, you will be going up. So this might be a way that we could perhaps find transition states, and we'll talk about that in a little bit later. But right now I just want to introduce you to what does this algebra tell you to do and what are the consequences of it. So the consequences of this kind of step was the energy will go downhill along all those modes, those directions in other words, that have positive curvature. Say, okay, that's pretty good. And just parenthetically, once you've solved for this delta VAs, we had earlier an expression that allows you to express what is the change in the Cartesian coordinate for delta xk as a combination of these delta VAs times the components of these eigenvectors of the Hessians. So this is how you would go back to tell the Gaussian program how to change each atomic coordinate, Cartesian coordinate, by a certain amount, given a certain amount of this delta VA. Okay, so just to summarize what we have so far. If you want to find a minimum, the best thing you ought to do is you take this displacement that formula just told you, as long as the direction is having a positive Hessian eigenvalue. If you find a direction that you're sitting at right now that has a negative Hessian eigenvalue, you don't do that, but instead what you do is you take a step in the opposite direction that's small. Because if you want to find a minimum, and you happen to be in a place where there's a negative curvature, along that direction, the worst thing in the world you could do is to take this step because you go up along that direction. So you say, no, I don't want that. If I want a minimum, I better go backward along that direction. So along each direction, you or the program has to make a choice. You say, okay, I have a certain direction. If this direction is positively curved, I will use this formula and I will go down. Along that direction, if the thing is positively curved, I'll use that formula and the energy will go down. Along that direction, if the thing is negatively curved, I'll use the opposite of that formula and the energy will go down because the lambda was negative along this last direction. So you have to make logical choices like that. The program does. Okay, so what about if you instead wanted to find not a minimum, but suppose you wanted to find a transition state? Well, what you want to do to find a transition state is you're after finding a point. Your goal in life is to find a point where all the gradient values vanish. That's either minimum, transition state, which is called first order saddle point. Second order saddle point with 2 negative degrees of freedom would also have all the gradient values vanishing. So you want to find a place where all the gradient components vanish and 3n minus 7 of the degrees of freedom have positive curvature and one of them has negative curvature. That's what your goal would be in life. So what you want to do then, and this is very, very difficult, so I just want to spend a little bit of time on this. That's ultimately what you'd like to do. But let me just take a concrete example here. In that blue surface that I showed earlier, if you happen to start out at a geometry that sort of was up near this transition state, where you could see that in one direction it was negatively curved, in other directions it was positively curved, that's usually the best case scenario, and that's why people usually try to make an initial guess of a transition state that is reasonable. So they'll sometimes take reactants and products and take a geometry that's somewhere in between, hoping that they already are starting at a point that has one negative direction and the rest positive. If that's the case, what you then do, if you want the transition state, is you take this formula, the delta VA is minus g over lambda, and you use it for all modes, because for the modes that are positively curved, you will be going to a minimum. I'm not talking about an absolute minimum. I'm saying that on the transverse degrees of freedom, you want to be at a minimum to be in this stream bed. But on the degree of freedom that is negatively curved, you also use this formula because for it, you will take a step that is not opposite the gradient, but actually along the gradient, minus GA over lambda. Lambda is negative, so you actually will go uphill, but that's what you want if you're trying to go to a transition state. So that what you do for transition state is if you're already at a point that has one negative curvature and all the rest positive, you use this formula for all modes, because along the one mode that's negative, you'll go uphill. For the modes that are negative, you will stay down in the stream bed, which is what you want to be doing. So this is a method for finding essentially stream bed walking toward a transition state. Now let me make a confession before I talk about the last part of this slide here. What a lot of people do when they try to use these formulas in geometry optimizations is they will take and they will say, I'm at a local minimum. I mean, let's just take an example. Suppose that you have a reaction that you're trying to study of an ethylene molecule and another ethylene molecule. We know that these two things come together and there's a barrier to the reaction, 2+2 cycloaddition. And suppose on one of these ethylene molecules, though, there happens to be a methyl group sitting out there. So you say, well, I bring these two things together and they form some weak van der Waals complex. And I do a geometry optimization and I find a minimum. That's probably this van der Waals complex. And then you say, well, what I want to now do is I want to go uphill along a stream bed to try to find the reaction transition state for squeezing these two things together to form cyclobutane with the methyl group sticking off the side of it. So the thing that a lot of people do is they'll take that van der Waals molecule and they'll go and calculate the gradient. They'll see it's 0. Good. They'll calculate the Hessian eigenvalues and see that 3n minus 6 of them are positive. They say, good, I'm at a minimum. And then the mistake they'll make is they'll say, I'm going to now find the Hessian eigenvalue that has the smallest magnitude, because they think this is the softest mode for going uphill. So if you're a hiker in the mountains and you're trying to find the lowest pass to get from reactants to products, you look around on your topographical map and you find and you try to see, well, the lowest pass I think is going to be, if I start out the valley that is the shallowest valley, it has the best chance to be a low pass. Now you don't know that for sure, because the valley could go on for a long time and become a very high pass. So when people do this, what they end up doing is, in this case, they say, let's take the lowest Hessian eigenvalue there, the softest mode, and they'll say, I'm going to take a step that's uphill along that mode and downhill along all other modes. And they think what they're doing is to find the transition state here. Well, in that case of the molecule I talked about, instead what happens is this methyl group sitting out here has a very low barrier to rotation. And all that'll happen is they'll find, that barrier to rotation has this sinusoidal threefold oscillatory barrier value. Indeed, they will find a transition state, but it will not be for the reaction. It will be for this rotation around the threefold barrier there. So that's why I say here that you must visualize the eigenvector belonging to any mode that you want to try to walk uphill along, and don't be stupid and find a methyl group rotation eigenvector and just try to walk uphill along that, unless that's what you want to find, the barrier to rotation. So what you have to do is you actually have to find some vibration of the molecule, some eigenvector, some distortion that has a lot of component that looks like this. And you can use things like the Gauss view or the Molden program to look at these eigenvectors. Okay, so what you want to do then in that case is you first have to start out very carefully, make sure you choose an eigenvector you want to go uphill along that makes sense to you, that's like this, not methyl group rotation. And then if you proceed like we talked about, where you take this kind of a step, you will actually go along a direction that would take, the energy change will be negative along all those directions that have positive Hessian eigenvalue, and will be uphill along any direction that has negative Hessian eigenvalue. This is an algorithm you can use for finding minima or for going uphill along transitions, reaction paths, stream beds as we call them, to find transition states. Okay, so that sort of is a strategy for what I've talked about so far, energy minimization and finding transition states. The next thing I want to tell you about a little bit is you can also use the same information to get harmonic vibrational frequencies. So far I've been talking about, we have these curvatures that are positive or negative, but there's a little bit more to harmonic frequencies than just the force constant, the curvature of the potential energy surface along a certain direction. There's also so-called reduced mass. Remember, harmonic oscillator is The frequency is h over 2 pi, square root of force constant, divided by reduced mass times v plus a half. So how do you actually get frequencies? Well, to get frequencies using the same information, you say, well, if we think about a molecule sitting at a minimum, and we think about this molecule vibrating around that local minimum, so all the nuclei are moving, they're undergoing vibrational motion. What kind of dynamical motion is that? Well, it's a dynamical motion where at the point we're at, our reference point where this delta xk and delta xl are 0, that is where the geometry we're at now, is presumed to be where the gradient vanishes. That's our reference point. That's our minimum. And here we say, let's consider a classical Hamiltonian that essentially just says we have a potential energy that's 1/2 the summation over k and l, hkl, delta xk, delta xl. So hkl, the Hessian, is the second derivative of the energy with respect to the displacements. Why is there no first derivative here? Because the point we're sitting at now, by assumption, has all the gradient components 0. We're at a minimum. So the total Hamiltonian for classical motion will be potential, which is going to be this harmonic potential that we represent through the Hessian. And then each of the nuclei will also have kinetic energy. So here we have 1/2 summation over k, mass of nucleus k, times the time derivative of nucleus k's position with respect to time, this time derivative squared. So 1/2 mv squared. Now, this would be the classical Hamiltonian, kinetic energy plus potential energy. The thing we do now is we want to convert this thing into something where there's not off-diagonal stuff. So what we do is we make 2 steps. We're going to do what is called introducing mass-weighted coordinates. So up here, those delta XLs mean the Cartesian displacement of component K. So what we do is we say, let's define a thing called delta mass-weighted xk to be just the square root of the mass of nucleus K. Now, in, say, an HF molecule, we would have 1, 2, and 3 would be the x, y, and z coordinates of atom 1, hydrogen atom. 4, 5, and 6 would be the x, y, and z coordinates of the second atom. So the mass of coordinate 1, 2, and 3 would be the same, mass of a hydrogen atom. The mass of coordinate 4, 5, and 6 would be the mass of a fluorine atom. Okay, so what we would do is to define new coordinates that we call mass-weighted coordinates in terms of the original coordinates like that. This Hamiltonian then, when expressed in terms of mass-weighted coordinates, you just plug that in, would still be 1/2 sort of mass-weighted Hessian, which is just the original Hessian times the square root of mass k, square root of mass l to the minus 1/2. So that's just as sort of trivial. And then times delta mass-weighted coordinate, delta mass-weighted coordinate. Okay, that looks like it makes things a little bit more confusing, but here's the main thing that happens. In the kinetic energy, when we do that, these changes in Cartesian coordinates, time derivative of xk squared, when we introduce these mass-weighted coordinates, it becomes 1/2 the summation over k of time derivative of the mass-weighted coordinate, its velocity squared. There's no mass anymore in the kinetic energy. It makes the kinetic energy as if it's what we call isotropic, that it's the same for all degrees of freedom. Okay, so we're not quite done yet. Then the next thing we do is we say, okay, we've made the kinetic energy look simpler here, not depending on mass. It's the same for all degrees of freedom. But the potential energy still has off-diagonal junk in here. So then what we do is we introduce the eigenvectors of the mass-weighted Hessian so we can express, just like we did before, the changes in the x, y, or z coordinates in terms of changes in the eigenmode coordinates. So we introduce these eigenvectors of the mass, now they're eigenvectors of the mass-weighted Hessian, not the original Hessian. And we can express these delta x's. So the bottom line is we can re-express that Hamiltonian as a summation of 1/2 lambda a. Now this lambda a is not the eigenvalue of the original Hessian like we talked about before. It's eigenvalues of this mass-weighted Hessian. Just to remind you, what's the mass-weighted Hessian? It's nothing but the original Hessian just multiplied by 1 over square roots of the masses. So on the diagonal, it would just have 1 over mass. On the off diagonal, it would have 1 over mass of one thing, 1 over mass of the other, square root. So it's just trivially calculated from the Hessian. So the Hamiltonian then would be the following. It would be summation over each eigenmode of 1/2 lambda a, eigenvalue of the mass-weighted Hessian, times delta VA squared, plus 1/2 the velocity along that delta VA coordinate. So now again we have the Hamiltonian separated into independent non-interacting, that is, no off-diagonal elements. So we can pretend that each one of these directions labeled A is a dynamical motion along that direction. So for example, this says that I have 1/2 times velocity squared times unit mass. I have a particle moving that has unit mass in a sense. It has a velocity along the 8th direction, and it has a potential energy that's just 1/2 lambda A times VA squared. It's a harmonic oscillator. So there are just a bunch of harmonic oscillators along each independent direction. The only problem is, I said it's a harmonic oscillator, and that's true as long as all these lambda A's are positive. So if you're at a minimum where all the lambda A's are positive, all the directions are positively curved, then yes, and that's where we usually do vibrational frequency analyses. You basically can say that each direction then is a harmonic oscillator, and therefore the frequency along each eigenmode is nothing but, if this was 1/2 mv squared plus 1/2 lambda x squared, you would say that's harmonic oscillator. So the formula for frequency would be the square root of the lambda is the force constant, divided by the mass, but the mass is 1 here in these units. So essentially, when programs go and calculate vibrational frequencies, all they do is take the original Hessian matrix, multiply by those square roots of mass factors to get the mass-weighted Hessian, find the eigenvalues of the mass-weighted Hessian, and take the square root of them, and they report those as the harmonic frequencies. So this is how programs calculate harmonic vibrational frequencies. Okay, now one more thing that we need to do here about reactions is we know how to find minima, we know a little bit about transition states, we know harmonic frequencies. How do we get reaction paths? Because reaction path is a hike in the mountains. It's a path that starts out at a local minimum of a base camp. And it goes up some stream bed. Now up a stream bed, as I go up the stream bed, the gradient is no longer 0 because I'm going uphill. Originally, the curvature on this stream bed is positive because I'm going up. If I'm in the stream bed, then transverse to me, the curvature is positive, and if I'm right in the stream bed, I'm at a minimum on this transverse degree of freedom. So the gradient is going up and up and up and up, and if I'm successful and find a pass, I eventually go up to a point where the gradient goes up, and then the curvature starts to turn over and become negative, like this. But still, if I'm in the stream bed, I'm still at a minimum transverse to that. So the stream bed goes up, and I follow it, and finally I get to a pass. And at the pass, I'm at the transition state. So just to do a reaction path, what one does is, like I talked about some time ago, you try to find a point where there is a Hessian eigenvalue that is negative. So you try to find somewhere where there's a negative eigenvalue of the Hessian. And what you do then is just follow these steps like I talked about before, that what you would do is you take this point, you go uphill along the direction where the Hessian eigenvalue is negative, and along directions that are transverse, that is the other eigenmodes, you try to do this minimum thing. And you can follow a reaction path that way. So what you do just algorithmically is you try to take small steps downhill along all the directions that have the negative Hessian eigenvalue. Oh, I'm sorry, I apologize. This is something what we're trying to do now is once you find a transition state, it's easier then to trace out reaction paths as follows. At the transition state, you find the eigenvalue that is negative, and you take a step downhill along that eigenvector, and that is like an initial step. And then what you do is you go down that stream bed, and transverse to the stream bed, you take these steps, delta VA is minus GA over lambda, to keep you in the minimum, that is to keep you at the stream bed. And what you're trying to do is to always go downhill along the direction that has negative curvature, and you can identify that also as the direction where the gradient is non-zero, because as you're going downhill, once you find the transition state, the gradient will become stronger, 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 and of course it'll get smaller and smaller and smaller as you approach the minimum. Now, one thing I should say about this reaction path following is, once you've found a transition state, and you might have found it by starting at reactance and struggling your way up to the top of the hill to find a transition state, the wise thing to do is at that transition state, you want to go downhill to products in the way that I just talked about, by taking these steps down the negative curvature direction where the gradient is, and staying in in the valley floor in the stream bed transverse to that, to the products. But it's also wise to go back to the transition state and go downhill back to the reactants by going down, down, down along the eigenvector. It's the same eigenvector, but it's in the opposite direction. It's leading you back to where the reactants were. Because in that case, what you're trying to do is to go downhill now all along this direction and downhill along the transverse degrees of freedom to remain in the stream bed. So it's usually easier to go down from the transition state than to crawl your way back up to the transition state. And it's good to do both of them just to make sure you get the same answer. Okay, so that's enough about just how you use information about gradients and Hessians to find transition states and minima and trace out reaction paths. Now what I want to do is to change the discussion a little bit into, well, where do these gradients come from in the first place? And of course they come from their derivatives of the energy, in this case with respect to the x, y, or z displacements of various nuclei. So for example, what you do to actually derive the equations for these gradients, and people have done this over the years, and they're available for various kinds of wave functions, for MCSCF and for SCF and for CI and so forth. You say, okay, I want to write down my energy expression. So for example, you might write down psi h psi over psi psi, that's my energy, and you differentiate it with respect to x, the Cartesian coordinate of xk, for example. Now the catch is, what changes when I move the Cartesian coordinate xk? Well, in principle, what changes is, in psi, there are some CI components. You know, the psi might be, for example, a summation of CI times determinant I. And so what changes is those CI components might change. So you write down, using the chain rule, dE dCi, dCi dx. But in the psi, there's also molecular orbitals. Those determinants contain molecular orbitals that have MO coefficients. So we have dE, dMO coefficient dx. And then also, we have in the Hamiltonian, you say, wait a minute, where does these nuclear positions occur in the Hamiltonian? Well, in the Hamiltonian, which involves the kinetic energy of the electrons, that doesn't have any reference to nuclear positions. Electron-electron repulsion, that has no notion of where the nuclei sit. But then it has the terms that are like minus the summation over all nuclei, charged nucleus, divided by the distance from nucleus A to electron I. That's where the nuclear positions occur. So that's what I mean by this dH dxk. It's the derivatives of the Hamiltonian with respect to the nuclear positions. And it's in those electron nuclear attractions is what would contribute to this dH dxk. Now, I want to just spend a little bit of time showing you that certain things are easy and certain things are hard. That horrible expression there with the chain rule for the gradient. You say, God, how am I going to get all those terms? Well, one thing is, if you happen to be doing an MCSCF calculation, you know that you've already made the energy minimum with respect to the CI coefficients and with respect to the MO coefficients. That's how you got the equations that MCSCF theory used to calculate the CI and MO coefficients. So in MCSCF theory, these first two terms, dE dCi and dE dMO coefficients, vanish. So all you really need to do to get the gradient in MCSCF theory is to deal with this last term in here. Likewise, in Hartree-Fock theory, number one, there are no CI coefficients, and number two, you've made the energy minimum with respect to these MO coefficients, so you've got dE dMO coefficient being 0. So again, in Hartree-Fock theory, you have to just deal with this last set of terms here. In CI theory, that is, if you're doing a CI calculation, you have made the energy with respect to the CI coefficients equal to 0, so the first term vanishes, but the second term doesn't, because you did not minimize your CI energy with respect to the MO coefficients. You got the MO coefficients from a Hartree-Fock calculation earlier. So in CI theory, you do have to deal with these terms that we call the response terms, that is dE dMO coefficients. You are going to have to do something about that. So let's just go and take a little bit more detailed look at this. When we're doing this psi h psi, I want to talk about these terms that are psi and then derivative of the Hamiltonian with respect to coordinate psi divided by psi psi. What are they? Well, psi, of course, is a linear combination of CI coefficients times determinants. And each of those determinants involves some molecular orbitals. And so those matrix elements of that Hamiltonian between the two determinants get expressed by the Slater-Condon rules in terms of molecular orbitals and kinetic energy and nuclear attraction, nuclear repulsion, electron-electron repulsion. But the bottom line is that there's only one place that the positions of the nuclei really are coming into bear here. Actually, there's two places. In the electron nuclear attraction, as I said, there's charge of nucleus, and then there's distance of electron to nucleus A. So that's one place that has to be differentiated with respect to the x-coordinate of the nucleus that we're doing the displacement of. But there's also another place, because in these MO coefficients, in these molecular orbitals phi m, they are themselves a summation over mu of Cm mu times chi mu. Now, in the earlier slide, I explained that you don't have to deal with the dE, dCm mu things, but those basis functions, they depend upon where the nuclei are sitting. So there are going to be some contributions that arise from taking the derivative of the energy with respect to the basis functions. Okay, so let me just talk a little bit more about this. The first thing is, how does that electron nuclear attraction potential, what's its derivative with respect to the 8th Cartesian coordinate? That is, now in the electron nuclear potential, of course, is the sum over all nuclei, charge of nucleus, E squared over distance from electron to that nucleus. If we're differentiating with respect to the x, y, or z position of that 8th nucleus, those are the only ones that contribute there. And when you differentiate something that's 1 over r, you're going to get something that's 1 over r cubed and then times this x up here. So there's a way you would sort of do this in your head, as you'd say, the 1 over r minus ra that's in the potential, you think of that as 1 over the square root of x electron minus xa squared plus y electron minus ya squared plus z electron minus za squared. When you differentiate that with respect to the x position of nucleus A, you would get from the denominator there, you would get some, basically called 1 over this square root thing, and you take the derivative and you get 1 over the thing to the 3 halves. So that's this 1 over r cubed. And then here you get x electron minus x of nucleus A. So that's what comes up in the numerator. So this is the expression for the derivative of the electrostatic potential of the electron and nuclear interaction with respect to the position of nucleus A's x-coordinate. Okay, so that's what you would have to deal with when you're taking that derivative. So what you have to actually end up doing when you do these gradient calculations is you have to evaluate matrix elements between molecular orbitals. Why do you do that? Because the energy expression that you're differentiating involved these Slater-Condon rule matrix elements that involve these MOs, but in the middle now are these new formulas, not the electrostatic potential, but it's this ZA, x minus XA divided by distance of electron r to nucleus A cubed. So there's these new integrals that one has to program up in the computer and do them. These are called the Hellman-Feynman integrals. So this is the so-called Hellman-Feynman contribution to the gradient. There's a little bit more to it, though. When you get down to doing these, when you did all the Slater-Condon rules, and we go back to this slide here, and you had energy expressions that involve these 1 and 2 electron integrals, not only did you have to differentiate this electrostatic potential that I just did for you, but you also have to take the derivatives of these molecular orbitals, not their MO coefficients, but the basis functions. They also depend upon where the nuclei sit. So you have to take, for example, these kinetic energy integrals, as well as the electrostatic electron, where the electron is interacting with nucleus A, for example, the electron-electron interactions. All these integrals here that involve basis functions, they have to be differentiated with respect to the position of the nucleus K. And what does it mean to differentiate that? Well, these basis functions, these chi's, are Gaussian functions. Remember, these chi's are functions that are these Cartesian coordinates, Gaussians, that are sitting at certain nuclei. They have to be differentiated with respect to the x or the y or the z coordinate of the electron relative to that nucleus. So those derivatives of those basis functions will give rise to new functions that have to be included in the calculation. So we say that out of these, for example, these 2 electron integrals that used to be just chi nu, chi eta, chi mu, chi gamma, the 2 electron integral there will be new integrals that will be involved with, for example, derivative of chi nu with respect to distortion of the position of particle K. So there are new so-called integral derivatives that come into these calculations. So the bottom line is, and there's good news and bad news. The good news is that if you're doing a CI calculation or an MCSCF calculation or an SCF calculation, in the gradient expression, the first 2 terms you don't deal with. The last term there involves this Hellman-Feynman contribution that involve just these derivatives of the nuclear attraction potentials and the integral derivatives that come in. So, first integral derivatives of these basis functions. But people have done this, and this is routinely available in most computer programs now. If you do SCF or MCSCF, gradients are easy to calculate. The problem is, though, that what about CI or Møller-Plesset or coupled cluster theory wave functions? The difference there is that in the total energy expression for the gradient, in the CI, the first term vanishes, as we said before, because dE dCi vanishes. It was equal to 0. That's how you derive the CI equations. But dE dMO coefficient doesn't vanish. So for CI wave functions, you have to do the Hellman-Feynman terms and the integral derivative terms, and you have to deal with these dE dMO coefficients in a way that I'll be telling you about in just a minute. In MP theory, you don't have these CI parameters, but still you have the energy written out in terms of, if you remember the expression, the Møller-Plesset terms had Hartree-Fock energy, and then they had these 2 electron integrals squared divided by orbital energy denominators. So there's analytical expressions for the energies, and you have to go in there and differentiate those expressions with respect to the Cartesian coordinate that you're differentiating with respect to here, this xk. So you have to have formulas for how do the orbital energies and how do the 2 electron integrals, the basis functions and the MO coefficients, vary with respect to these xk's, and I haven't yet explained that. For coupled cluster theory, it's even worse, because coupled cluster theory gives the energies with respect to these T amplitudes, which you've probably forgotten about, and you have to have expressions for dE dt amplitudes, and then dt amplitudes, the xk. So you have to derive expressions for these things. So they're not trivial. So the new things are the MO coefficient dxk and dt amplitude dxk. They're called response equations. And I just want to give you a flavor of how you get these things. For example, when you're doing CI type gradients, we have to know what is the derivative of the MO coefficients with respect to the xk's. How the hell do we get that? Well, we go back to the equations that determine the MO coefficients, which is the Hartree-Fock equations that I've written out here. See, Fock matrix times C equals epsilon times overlap matrix times C. We differentiate that equation with respect to the xk's. That's an equation we will use to get dC dxk. So we differentiate that, and what do we get? Just without the indices, just follow the basic idea here. If I take the derivative with respect to xk of the first terms on the left-hand side, I get 2 kinds of terms. I get Fock matrix times dC dxk, and another term that gives dC dxk comes from the right-hand side, minus epsilon overlap matrix times dC dxk. So those terms are the ones that are dC dxk. Then I also get terms that involve just C, where the derivative acts on the Fock matrix. So I get, for example, d Fock matrix dxk times C, and I get minus the derivative of epsilon times overlap times C. So I get basically 2 kinds of contributions, one involving derivatives of things I already know, the Fock matrix and the orbital energy, times the C, and then the other part is Fock matrix minus energy times overlap times dC dx. And I solve that for see, there are a set of linear equations, and I can solve that for these dC dx's in terms of things I already know. So basically, these response equations can be derived. They still involve new derivatives, because these terms that involve derivatives of the Fock matrix, derivative of the orbital energy, derivatives of the overlap matrix, they do involve derivatives of basis functions. So new things have to be programmed into the software. But the bottom line is that you can solve these so-called response equations for derivative of MO coefficient with respect to xk. But they have to be done for the CI, for example. Now for coupled cluster, I don't even want to go into it because the philosophy is still the same. You write down the equations that are used to determine these T amplitudes. You differentiate those equations with respect to xk. You get equations then for dt amplitude dxk, which can be solved. It's a nightmare, but they can be done. So the bottom line is that gradients these days, derivatives of energies with respect to nuclear distortions, and even Hessians. I didn't even go through second derivatives. It's worse. But the basic idea is still the same. You write down an energy expression that you're going to use for CI or Hartree-Fock or MCSCF. You take second derivatives and you work through and see what kind of new integrals arise. You have to program those up. And they can be done these days. Now I want to close out this session with a discussion of a different kind of response, just very briefly. This won't take nearly as long and it won't be as, let's say, burdensome or complicated. Another kind of response comes into play when one wants to, for example, and here I'm doing an example from spectroscopy. Suppose you have a molecule where you've got its geometry. You've optimized it and you know its wave function. And now you say, I would like to know, how does the energy of that molecule change if I apply an electric field to that molecule? So you say, okay, what I'm doing when I apply the electric field is I'm adding these last two terms I've written here to the Hamiltonian. So I have H is sort of like H0 plus V. I'm sort of thinking perturbation theory. So what I'm doing is I'm saying I want to calculate how the energy responds to the application of this term here. Now what is this term? It's essentially just a summation over all the electrons of charge of electron times position of electron dotted into electric field, plus the sum over all nuclei of charge of nucleus times position of nucleus dotted into electric field. That's just the linear electric field interacting with individual charges in my system. So what do you have there? You have a Hamiltonian that was your original Hamiltonian plus this response term, this term that you added to it. And in principle, what you're trying to do now is you're trying to write down what would be the energy of the system with this H plus electric field term. So you write down essentially psi H psi over psi psi, and pretend you're doing Hartree-Fock or MCSCF so we don't have to deal with these response terms. But in principle, you would have psi for the wave function with the field applied, H of the wave function with the field applied, psi of the wave function with the field applied, which you don't yet know, divided by psi psi. And you would say, I want the linear derivative of that. I want dE, the electric field. Well, you would say that's dE, dCi, dCi, the electric field. dE, dCi is 0 if I'm doing MCSCF or Hartree-Fock, so let's do those. Then I'd have dE, dMO coefficient, the electric field. Let's say we're doing Hartree-Fock or MCSCF, so dE, dMO coefficient is out the window. Say, thank goodness. But we'd still have psi with the electric field gone because we're doing just the linear, we're taking the first derivative at electric field equals 0. So this would be psi at electric field 0, the wave function you already had. This would be dH, the electric field, psi. So we'd have to evaluate this kind of thing here. Now you say, oh, that's nothing new to me because the derivative of the Hamiltonian with respect to the electric field, the only place the electric field appears is in this linear term I've added. So I would just get the summation over K of E RK plus the summation over nuclei of E ZA times RA. Holy schlamoli, that's just psi, dipole operator psi. So you say, oh, that's neat. I knew that formula all along. The derivative of the energy with respect to electric field is nothing but the expectation value of the dipole operator. And that's how you get dipole moment. But, and this is the last thing, what if you said, I'm not doing CI, I'm not doing MCSCF, I'm not doing Hartree-Fock, I'm doing CI. So if I want to do a CI determination of the energy response with respect to electric field, I will have to include this first, the second terms here, dE, dMO coefficient, dE. So in that case, the formula for dE, the electric field, will end up being expectation value of the dipole moment operator plus a response term here. Now you say, well, why is that important to talk about, Jack? Because what this essentially means is the following. If you want to calculate the dipole moment of a molecule using a CI wave function, it's not proper to just calculate the expectation value of the dipole moment operator for the CI wave function. You have to throw in also this response of the energy with respect to MO coefficients, the electric field. Those response equations have to be solved. So you say, wait a minute, I don't believe that because Michael Morse taught me in spectroscopy or in quantum that the dipole moment is always psi, dipole moment operator psi. So what's right and what's wrong here? Well, the stuff that Michael Morse taught you assumed that the psi you were using was an exact psi here. See, what we're saying here is the response of the energy with respect to electric field, if you're doing a CI wave function, will not just be the dipole moment expectation value, but will be these extra terms. And that actually is the right answer because the way that a dipole moment really gets measured, as I talked about earlier in this session, is a molecule gets passed through an electric field. It's inhomogeneous. That is, it's spatially inhomogeneous. It's stronger over there than it is over there. As the molecule goes through there, the electric field does change the energy of the molecule, but it changes it differently in this region of space where the electric field is stronger than in this region of space where the electric field is weaker. As a result, the electric field applies a force on the molecule. Force is dE, d position. So in other words, the electric field being stronger here than over here will pull the molecule to one side. It will deflect the molecule. So the experiment that measures dipole moments is always based on the deflection of a polar molecule in an inhomogeneous electric field. That then comes back to how does the energy of the molecule vary with electric field. The energy varying with respect to electric field is exactly what the dipole moment measurement does. And in a CI wave function, the energy varies with electric field not just in this expectation value way, but also in this response equation way. So in the literature, if you find papers that are published where they say we did a CI calculation, and then we evaluated the dipole moment by just calculating expectation value of the dipole moment operator, they're not right. These response terms also have to be put in there, and they can be significant. And that's something that I think very few people are aware of, but more people should be aware of these things. So one of the advantages of doing MCSCF and Hartree-Fock is these response terms contributing to the first order responses of the energy with respect to any kind of distortion or electric field vanish. In those cases, the expectation value type formulas are what you really need to use. But in cases like CI and Møller-Plesset perturbation theory and couple cluster theory, where these response terms are not zero, it's not proper to evaluate things like dipole moments just with expectation values. But most people still do it this way, and they're wrong to do that. So that's the end of session 12.